Hello everyone and welcome to the second video in the two-video series exploring the check valve design project sponsored by Zurn Wilkins in Paso Robles, California for the Senior Design Series in the Mechanical Engineering Department at Cal Poly San Luis Obispo. The team members of this project include Jessica Dent, Skylar Testing, as well as myself, Alec Dermatoyan. The goal of this project was to produce a check valve design and prototype that would lower the pressure loss comparative to existing Zurn check valve products. The design process that our team adopted was an iterative design, build, and test cycle. Early models of the double disc included static designs where steady-state testing was conducted as a baseline, and later on, final prototyping integrated torsion springs, dynamic valve poppets, and functional seals.
So here you can see a picture of our final design. This has two identical check valves. This is for ease of manufacturing as well as ease of replacement and maintenance on the valves. The valves themselves are in yellow and orange, and they're separated by that purple spacer. We first printed the components on Zurn's 3D printer out of SLA, and then sanded away any interferences that came due to the tolerance of the printer. He then inserted the pins to hold back the poppets and the springs, and then inserted that whole assembly within the check frame. This then had all of the seals inserted, and then the whole frame was placed in the backflow housing for testing. In our proposed final design, the check hinges in yellow feature a dovetail groove which helps hold the seals in place. The spacer acts as a sealing surface between the upstream and downstream check. Finally, the poppets are held back by the torsion spring, which is rated to meet standards in industry for fatigue.
In order to test our designs, we use Zurn's wet lab facility. The test apparatus is composed of a storage tank that circulates water in a closed loop. This is where we install the check valve to be tested. We use this needle valve to control the flow rate throughout the test, gathering data at approximate intervals of 10 gallons per minute. The pressure is recorded from the pressure differential gauge in PSID, and the flow rate is measured through the magnetic flow meter, or magmeter. The primary engineering analysis we performed was with CFD, or computational fluid dynamics. In this first render, we can see a cut plane of the test stand with no check valve installed. The purpose of this simulation was to determine the validity of our model by comparing it to physical test data. Our simulation came within 4% of the test data. Colors here represent the pressure gradient across the valve. These next two renders show the pressure gradient across the V6 prototype in a static configuration, one at 45 and the other at 90. This simulation is a transient model and has flow-driven angular motion defined for the poppets. The torsional spring was modeled with a resistive element and appropriate parameters. This model was able to closely replicate test data to within 20% error. Here is an animation of the transient model. This cut plane shows the velocity field developed with both vectors for direction and color for magnitude. The presence of vortices can be observed.
Unfortunately, the COVID-19 situation severely reduced our potential to progress the project to where we wanted it to be. This is because our project's forward progress heavily relied upon live test data results to drive the next design changes of the check valve. Regardless, we believe that the work we have completed serves as a strong foundation that Zurn engineers will be able to build off of in order to integrate the double disc into an operational check valve for water supply lines. Please feel free to explore our project webpage for further information. We would once again like to thank our sponsors at Zurn Wilkins, including Brian Yale, Ruben Westmoreland, and Chris Corral, as well as our senior project advisor, Sarah Harding, for making this project possible.